Okay, so in this video, we will tackle the subject of logarithmic differentiation. And the idea is the following. Some functions may be really hard to differentiate directly, or just plain impossible. And surprisingly, with the help of logarithmic functions, namely, we will only ever use ln, so the logarithmic function base e, because quite simply it has the simplest derivative. Remember that the derivative of ln of x, the logarithmic function base e, is just 1 over x. We could use in our next examples any other logarithmic function, but as ln of x provides the simplest derivative, it is more natural to use ln of x and not other bases for the logarithm. Let's start with a few simple examples. Sorry about that, where we can differentiate the function directly. And then we'll throw a bit of a curveball. What if I ask you for the derivative of the power function x squared? Well, this is the simple power rule. The derivative of x squared is 2x. And we're done. So if you raise x to a fixed constant, the derivative is easily found with the power rule. What if we now flip the role of 2 and x? And what if we ask for the derivative of now the exponential function 2 to the x? So now, the difference from here to here is the following. When you have a power function, it is a variable raised to a constant function. An exponential is the opposite. It is a constant raised to a variable. And if you remember, the derivative of any exponential function is the function itself times the ln, the natural logarithm, of the base. The base here is 2, so it's 2 to the x times ln of 2. What if we have the following example? What if we ask for the derivative of x to the power x? Can we find the derivative of this function with our usual rules of differentiation? Well, we cannot use the power rule because the power rule requires x to a fixed power. The power here is a variable, so we can't use the power rule. Can we use the rule for exponential functions? The answer is no, because an exponential function has a constant base. The base here is changing. So this function is neither a power of x or an exponential function. So at this point, we have no idea how to differentiate this function directly. Well, do we give up? No. We can summon the power of ln of x. If you look at these properties, these are the 3 key properties of any logarithmic functions. But as you remember, we are only interested in using the simplest one, the logarithmic function base e, ln of x. So ln of a times b is the ln of a plus ln of b. Ln of a over b is the ln of a minus ln of b. And ln of a to the b is b ln of a. If you look here at this third property, this is the one we'll take advantage of, because the problem here is the exponent is a variable, and directly we cannot use either the power rule or the rule for exponential functions. So let's see now what we can do. Our function is y equals x to the x. Well, the two sides are equal, so we can take the ln of both sides. So the ln of y equals, well, we can now replace y inside the ln by x to the x, because y is equal to x to the x. So ln of y equals ln of x to the x. And now we can use the third property of logarithmic functions. We can pull the exponent outside of the ln. So ln of x to the x is quite simply, moving x outside, x times ln of x. And now look at what we have. Now we have ln of y equals x times the ln of x. And if you look at this, the problem has disappeared. There's nothing here that we don't know how to differentiate, so we can differentiate both sides, but remember that y is a function of x, therefore this is a function of x, this is also a function of x, so both sides are equal as functions of x, hence they have the same derivative. So we will use here implicit differentiation, and remember that what we want is the derivative of x to the x, so we're looking for solving dy over dx. Well, let's differentiate both sides of our equality. So we have the derivative with respect to x of ln of y equals the derivative with respect to x of x times ln of x. Let's differentiate carefully both sides. So, the left-hand side, this is ln of y. We have a composition, the outside function is ln, and if you go back up, the derivative of ln of something is just 1 over the argument. So here we have the derivative of ln of y. Differentiating the outside function by the chain rule, we differentiate ln, and the derivative of ln is 1 over the argument, 1 over y. But there's still a y left over. By the chain rule, we have to multiply what we have so far by the derivative of what's left over. What's left over is y, therefore the derivative is dy over dx. Now on the left-hand side, there is nothing left over, so we are done differentiating the left-hand side, equals. Now the right-hand side. Well, here we have a simple product between x and ln of x, and so we use the product rule. Derivative of the first function is 1 times ln of x plus the first function x times the derivative of ln of x, the second function, but the derivative of ln of x is 1 over x, and we can simplify a little bit. Ln of x stays ln of x, plus, well, x times 1 over x is just 1, so we have ln of x plus 1. So if we rewrite this, 1 over y dy over dx is simply ln of x plus 1. And now we wanted to solve for the derivative of our function dy over dx, and this is done by multiplying across both sides by y. If you multiply the left by y, this will cancel by this. And now we have dy over dx. The question is, can we find the derivative as a function of x only? Well, if you remember, y was x to the x. So we can replace now y in here by x to the x, and so the derivative dy over dx is ln of x plus 1 times y, and y, as we've just stated, is x to the x, so times x to the x. And so we can finally write, if you want to replace y in here, by its actual expression as a function of x, which is x to the x, we have our conclusion. The derivative of the function x raised to the power of x happens to be ln of x plus 1 times x to the x. And there you have it. This is the method of logarithmic differentiation. If you cannot find the derivative of a function directly, but you can use properties of logarithmic functions, properties of ln, to simplify the expression. And as we've done here, the idea was that we could pull the power down with the property of ln, and then we can differentiate. And you see in the end, you may ask, well, could we have avoided using ln? And as you can see, not really, because the derivative of x to the x, there's no ln here, and it crops up here. And that's not a coincidence. The only way you will differentiate this function is by using the logarithmic function ln, so log base e, and its properties. And this is really what logarithmic function is about. if you have a function that you cannot differentiate directly, but you can simplify with properties of ln, use ln, and then differentiate using implicit differentiation. Let's do a few more examples. Consider now the second function. Suppose we go with the function y equals x to the sine of 3x. Once again, here we have a base that's changing, that's a variable, and an exponent that's also a variable. So we cannot use here either the power rule or the rule of differentiation for exponential functions. But we know that we can take ln on both sides and then bring the power outside the ln. And this is once again an example where we can only find the derivative of y with respect to x using logarithmic differentiation. So ln of y will equal ln of the right-hand side, ln of x to the sine of 3x. Property of ln, we can remove the exponent outside of the ln, and we get sine of 3x times ln of x. And now once again we have two expressions that we can differentiate, keeping in mind y is a function of x, so here both functions are equal, therefore they have the same derivative, but because y is a function of x, when we differentiate this term, we'll have to use implicit differentiation. So the derivative of the left-hand side, which is ln of y, will equal the derivative of the right-hand side, derivative of sine of 3x, times the ln of x. Once again, we have a product, so we'll use here the product rule. As in the previous example, the derivative of ln of y with respect to x will be 1 over y, chain rule times dy over dx. This will be equal to, and here we use the product rule, and be careful on the sine of 3x, we'll have to also use the chain rule. Derivative of sine is cosine, so cosine of 3x, times the derivative of the argument, which is 3. And that's the derivative of the first function, times ln of x, plus the first function, sine of 3x, times the derivative of the second function, times 1 over x, but if you do times 1 over x, that's the same as dividing by x. And finally, we have our dy over dx, but it's multiplied by 1 over y. So all you have to do now is multiply both sides of the equality by y, and so 1 over y cancels. And as always, whenever possible, we want to express the derivative dy over dx as a function of x only. This will not be always possible, but in this case it is because y is x to the sine of 3x. So we now have our derivative. The derivative of the function y, which is x to the sine of 3x, is equal to, we can write this as 3 cos of 3x ln of x, so 3 cosine of 3x ln of x, plus sine of 3x over x, times y, but y we know is x to the sine of 3x. And there you have it. The derivative of the function x to the sine of 3x is this times the function itself. So in both cases, the first and the second one, it was impossible to find dy over dx, the derivative of the function directly, but after we take the ln on both sides and use properties of ln, then we get something that we can differentiate. We differentiate carefully with the chain rule and implicit differentiation, and finally we solve for dy over dx. Let's consider now just two examples where we do not have to use logarithmic differentiation, but where using it either way will save us a fair bit of work. So consider the following problem. Suppose we want to find the derivative of the following function. So y equals, and I'll give you a rather unpleasant quotient. So what if I say x squared plus 3 to the power of 8 times 6x minus 1 to the power of 9 over the square root, say, of x plus 2. Well, you could find the derivative of this directly. You have a quotient, use the quotient rule, but to differentiate the numerator, this will require you the use of the product rule, because there is a product here, and the chain rule on both of these terms. So this will be quite a lot of work directly. Let's now use properties of logarithmic functions, specifically ln, to simplify the expression and then differentiate using implicit differentiation. So here, as before, we want to find dy over dx. But remember here, and in this case we'll use all three properties. We want the derivative. So let's take ln on both sides and then simplify the expression. So we have ln of y will equal the ln of this expression. But think of it, this is the ln of a times b divided by c. So imagine that you have this ln of a times b over c. Well, properties of logarithmic function, this will be ln of a plus ln of b. C is on the bottom, so it will be minus ln of c. So we'll have here, ln of y will be the ln of this, plus the ln of this, minus the ln of this, but each time, you see, we have an exponent on the expression. Right here, this is just x plus 2 to the 1/2 power. And remember now the other property of the ln function, ln of, say, a to the b, that's just b ln of a. So now when you take the ln of this, simplify in just one go. Ln of a, b over c will be ln of a plus ln of b minus ln of c. So it will be the ln of this term. But we can move the exponent outside. So the ln of this will just be 8 ln of x squared plus 3. And that's it. Plus the ln of b, the ln of the second term. Once again, we have an exponent on the argument. We can move the exponent outside the ln. And so the ln of this will be 9 ln of 6x minus 1. Finally, this is on the bottom, so it will be minus the ln of this term, which is x plus 1 to the power of 1/2. Once again, move the power outside the ln, so the ln of this will be 1/2 the ln of x plus 2. And now that we have simplified, we can differentiate. And believe me, that differentiating these two expressions will be a lot simpler than differentiating this expression. So let's do this. Both sides again, y is this function of x. Both sides are equal as functions of x. So we can once again differentiate using implicit differentiation. Differentiate both sides with respect to x. The derivative of ln is 1 over what's inside, so 1 over y. Chain rule times the derivative of the inside, which is dy over dx. And that's equal to 8 is a constant multiple, so it just stays there, times the derivative of ln, which is 1 over what's inside, so 1 over x squared plus 3, chain rule, times the derivative of the leftover function. The derivative of x squared plus 3 is simply 2x. And we keep going. Plus, 9 is a constant multiple, so it stays there. The derivative of ln is 1 over what's inside. Chain rule times the derivative of 6x minus 1, which is 6. minus 1/2 is a constant multiple, it just stays there, times the derivative of ln, which is 1 over the argument, x plus 2, times, by the chain rule, the derivative of x plus 2, but that's just equal to 1. And we're done differentiation. So, as before, on the left we have 1 over y dy over dx equals this. If you want to solve for dy over dx, therefore the derivative of this function, multiply both sides by y, so y over y is 1, y here, and now we can write our final answer by cleaning up these fractions a little bit. So the derivative, dy over dx, the derivative of this function happens to be 8 times 2x, that's 16x, so 16 x over x squared plus 3, plus 9 times 6 is 54, so plus 54 over 6x minus 1, minus 1 on top, so minus 1, over 2 times x plus 2. And don't forget the leftover y. And as always, if we can, we want to leave y or replace y by a function of x. This is not always possible, but here it is. Y was this lovely function of x. So x squared plus 3 to the 8th power times 6x minus 1 to the 9th power all over the square root of x plus 2. And there you have it. The derivative of this function is this function. It's kind of a monster, but if you look at every step along the way, the first step wasn't too hard. We simplified the ln of both sides using the properties of logarithmic functions. And once this was simple enough, then we differentiated. This was actually very straightforward. And then we just isolate our dy over dx. Let's do one more example that will involve, right from the get-go, implicit differentiation, where the answer will, in the end, be a function of x and y. This will be our final example. So suppose we have the following curve, and this will be a curve because it will not be y equals a function of x, it will be an equation involving x's and y's. So what if we have this? Let's say y to the cos of x equals, say, sine of x to the power of y squared. So once again here, we cannot have y equals f of x explicitly, but we can still think of y as a function of x. Well, we can't differentiate this directly because it's a variable to the power of a variable, same thing here, so we cannot find dy over dx directly, but we know that with the help of ln, we can bring the exponents down. So as we did before, we take the ln on both sides. The ln of this, we can move the cos outside, will give us cos of x times the ln of y equals the ln of this, but we can also move the y squared outside, so we'll have y squared ln of sine of x. And now, with the help of ln, both sides can be differentiated, so let's differentiate both sides with respect to x, keeping in mind that we have to apply the product rule and the chain rule very carefully. This is cos of x times ln of y, so we use the product rule. Derivative of cos is negative sine. Oops, so we have negative sine of x times the second function ln of y plus product rule, the first function, cos of x, times the derivative of the second function. Keep in mind the derivative is with respect to x, so we'll have the derivative of ln 1 over the argument, chain rule, times the derivative of y, which is dy over dx. That takes care of the left-hand side. Now we differentiate the right-hand side, and once again we have a product, y squared times the ln of sine of x. The derivative of y squared with respect to x is 2y, chain rule, dy over dx, times the second function, ln of sine of x, plus product rule, the first function, y squared, times the derivative of the second function, ln of sine of x. So we use the chain rule here. The derivative of ln is 1 over what's inside, so 1 over sine of x. Chain rule, that is just the derivative of ln times the derivative of what's left over, which is sine of x. The derivative of sine is cosine of x. And now we have the derivative. So all that's left to do is solve for dy over dx. So we'll bring this term to the left, send this one to the right, and then isolate our dy over dx. So what are we going to have? Dy over dx times cos of x over y Now here we have 2y ln of sine of x times dy over dx. Once we bring this over here, this will be negated, so negative 2y ln of sine of x. That's the left-hand side, equals, well, this term, now if you think of it, sine over cos is tangent, cos over sine is cotangent, so we can write this simply as y squared cotangent of x. And this term now we send on the right-hand side, and it will become a plus sine of x ln of y. And finally, we can solve for dy over dx by dividing across by this expression. And so we'll get that the derivative of the curve, given by this bizarre equation, happens to be equal to y squared cotangent of x plus sine of x ln of y divided by, and here you can leave cos of x over y, or you could also say y to the negative 1 times cos of x. Doesn't matter. We'll leave the cos of x over y minus 2y ln of sine of x. And there you have it. The derivative of the curve given by this equation happens to be this expression of x and y. And you can ask in the end, can we give the answer only in terms of x? Well, that would require us to know what y is as a function of x. And if you look at here, we cannot solve for y as a function of x. So the best we can do is leave the final answer in terms of x and y. And this is logarithmic differentiation. So there are functions that cannot be differentiated directly. Then you have to use ln, as in the case of x to the x, or as in this case as well. But there are other functions, as in our previous example, where we had this nasty quotient with powers of polynomials, and then you could differentiate directly, but with the help of ln and the three properties, you can simplify the expression quite a bit, and then differentiate, which makes your life a lot easier. And that is logarithmic differentiation.